Excellent. And I'll first write, this is, can I think of this as tangent squared of x all squared? Tangent x, secant x, of course secant x, tangent x. And I can now write what? Secant squared x minus 1. I guess kind of this time this has a what? Alright. This is secant to the fourth, right? Tan x. Secant x. There it is. The lonely secant x tan x that we want to do the use of. So, hey, this is the use substitution right here. I can do it right now. It is ready. Let's do it. Here's what? U to the fourth, and that's the du. Du replace tan x, secant x right there. That's the du. U to the fourth. U squared minus 1 squared. What's that FOIL? U to the fourth minus 2u squared plus 1 times u to the fourth du. Oh, here we go again. U to the fourth times u to the fourth. U to the eighth. Yeah. Add exponents. Add exponents. Minus 2u to the sixth. Add exponents. That's just u to the fourth. So I get u to the ninth over 9 as the antiderivative. Minus 2u to the 7th over 7 plus u to the 5th over 5 plus Charlie. And I'll put the u's back. Secant 9x minus 9 minus 2 secant 7th x over 7 plus secant x. 5, let's see. Ooh. Awesome. Great job. Seriously, one really good job with this. We have still yet to use those power reducing identities. Okay, those come up next. Yeah, be careful on something like this. I mean, it looks like, compared to the problem we just did, this thing looks simple. It actually is, but just be careful. Too many times this can happen. Oh yeah, tan squared, yeah, that's like secant of x. Like, wait a minute, no, that's not it, right? Derivative secant is secant x tangent x, right? The derivative tangent is secant squared. It sounded familiar, right? Like this, isn't it? But this problem shouldn't be too bad. What if you just got a tangent squared x by itself? I think you'll find this one, compared to the last few, a lot quicker. But I do notice, everyone, if I can get a secant squared, or if I can get a cosecant squared, I mean, it's written that way, but what is the integral of secant squared of x? Yeah, just tangent x. I'll go over here to the side. What's the integral? I'll put plus c. What's the integral of cosecant squared of x, which is similar? It actually comes out negative. Negative cotangent of x plus c. So, daggone it, it's tan squared, but this one's a lot easier, as we can tell. Right? These are true. So how can I play with this at the beginning? These are one of the trig expressions. Let me knock this problem out. Everyone saw this, brilliant. They said just make the trig identity, using the trig identity, secant squared x minus 1. Right? And you're like, there's no use up here on this one compared to the other ones. That's just equivalent to this by the trig identity. This one. Cool. And now we're ready to can I just rewrite this as integral secant squared of x minus integral of 1? Right? So if you want to do this, some don't, but if you want to think of this as, okay, I got that integral. Easy. Minus the integral of 1. Easy. No use of. So what's that integral? Yep. And what's the integral of minus 1? Is it 0? There you go. Right? So that's my point. Sometimes the easiest problems could be the one that stumps you. You're like, what do I do with this? Seems like it's impossible. It's like, oh, wait a minute. If I can just get everything in terms of secant squared of x alone, cosecant squared of x alone. Okay. So my point is, something like the integral of cotangent squared of x would be very similar with it because of this identity right here. If you had to do just the integral of cotangent squared of x dx, it would be very similar to that. All right. Well then, so we're looking at just isolated trig function squared. Now it's time for this. And if you just have to do the integral of cosine of squared of x or sine squared of x from here on out, use the power reducing identity. So if you ever see this, it's going to come up from time to time, especially this section. Especially this section, you go, I just need the power reducing identity. I just need to know it. It's equal to 1/2 plus 1/2 cosine of 2x. Use the power reducing identity. Some of you probably factor out the half. And I usually do the same thing. I'm going to be honest with you as I write this all out. That I leave the halves inside. I just factor out the half. I worry that one can bug a student. Then they got to distribute the half at the end. I'm like, I'm just going to take care of this right now. Now this problem's a piece of cake. What's the integral of a half? 1/2 x. That's my point. My goodness. This does require a use up here, though. You see this right here? I'd have to let the u equal 2x. Then that 2 pops out, and this becomes what? 1/4 sine of 2x. I probably don't have to write that every time today. I should write it on this first one. Just because I don't want people going, how the heck did you do that? This right here, when I take that integral, I do have to do a u sub, but I only let the u equal to 2x. You go, really? Yeah, because in terms of, I mean, u equal to the, with this, you'll notice I'll just get u equal to this 2x. You go, why just that? Well, look at this. What's du? 2 dx, or 1/2 d equals dx. So in this case, 1/2 times a new 1/2 makes it, yep, the integral of 1/4. All right, this becomes, that was done. I'm still working on this guy. The integral of cosine of u du, 1/2 times 1/2 became a what? 1/4. Good. But do you agree that's done? That 1/2, we're done with that. I'll just keep carrying it. We're just playing with the second part. This part. Okay, what's the integral of a cosine? Sine of u. Now we substitute. And what do you have? 1/2 x plus this. I get 1/2 x plus 1/4 Sine of 2x plus c. Hey, not to confuse anyone, I just wanted to point out here that we knew this was just going to be a simple integral 1/2, 1/2 x. So I just kept carrying it. The focus was that second part. Now that means the integral of sine squared of x should be identical. The same answer, except for that symbol. And when I want you to spot this, you can look at all these steps. View the integral of sine squared of x. Look at its power reducing identity. It's identical except for the what? The plus versus the minus. So its final antiderivative, the integral of sine squared of x, should be identical except that should turn into a what? A minus. No? You just want to make that note. Sure, Sean, go ahead.
Because isn't the difference
Oh, and let me,
when you do that? No.
this is a cosine, my apologies. Everyone, hey, shame on Professor Messenger. I did not do that on purpose. I know. That's probably into like 45 minutes of the video. My apologies. I didn't do that on purpose. These are both cosines. Right there. Cosine of both of these. The power reducing identity. All right. So if I do the integral of sine squared of x, should it be the same? Except for what? That becomes a minus. Okay. So we got that, but now here's the next one. How do you deal with this? What about a scenario like this? I've got the integral of x times sine squared of x dx. What can I do with this? So I'm looking at this thing going, can I still use the power reducing identity? That's what we want. So when you just have cosine squared of x, or you just have sine squared of x in the integral, we're going to use the power reducing identity. What if you have a sine squared of x with a lonely like x here? I'm still going to apply the power reducing identity. So I'm just going to put x, and what will this be? 1/2 minus 1/2. Again, my apologies. This is a cosine of 2x dx. Yeah, that's a cosine. Okay. Well, before this becomes confusing, can we distribute that x? I've got an integral of 1/2 x. That's not going to be hard, is it? Up with the x. Minus, you've got an integral of 1/2 x. So pull that half out of there. X cosine 2x. We can get these out of the way. But look at this carefully. And when I distribute the 1/2 x, distribute this x over here, x cosine 2x, there was that half with this, and I'm just thinking of these as two separate integrals here. Well, that's easy. What's that? X squared over 4. We got that down. That is not a use of, but it's something that we're familiar with, especially from the last test. What method? Integration by parts. I'm going to put an IVP here, everyone. Great eye. Those of you who recognize that. That's integration by parts. That's not a use of. This is going to be easy. We know that. If you want to finish that out right now, you can, but we're we're gonna have to do integration by parts. That's why I took the half out of here. So we can just go over to the side. U equals something. dV equals something because, remember, the integral of U dV equals ultraviolet minus the integral of voodoo, right? Flip it. What should I let the U equal? The X. Brilliant. So the dV is everything else, the cosine of 2x. What do? We integrate that and we differentiate that. So what's du? 1 dx. This dv is this cosine 2x dx, so what's v? There you go, chain rule, 1/2 sine 2x. Now you're getting used to these, right? They come up a lot. Alright. If you want, you can keep writing this, but this is already just what? What's the integral of that? That's x squared over 4? Okay. Minus 1/2. Sean, I'm going to do that bracket thing. Just so I'm very careful with this. And inside the brackets I do uv minus integral v du. Okay. Leave that minus 1/2 there. I'm getting x squared over 4 minus 1/2. In my brackets, I've got x times 1/2 sine 2x minus integral v du. Bracket. Shit, don't look like I see here. And I'm sure you're finding that last step pretty easy, right? We'll distribute that half to each part. All right. X squared over 4 minus, what's a 1/2 times a 1/2? 1/4 x sine 2x. And look carefully. Let me make sure you see these brackets here. That bracket extended all the way down here. And in front of this bracket or these parentheses is a minus 1/2. So what's a minus 1/2 distributed to a minus right there with another half? Plus 1/4 integral of a sine of 2x. This still has the integral on. But does everyone see I'm just being very careful with the distributive property? This thing, I want to make sure you knew that this race all the way from there to here, just like it did here. Make sure one sees that. That minus 1/2 has to get distributed there as well. If that's complete. That's complete. What's the integral of that? Negative cosine, yeah. And where's the 2 going? The denominator by the u sub? So I'm going to have to flatten this. I'm going to show this easiest. You've got final answer x squared over 4 minus 1/4 x times sine of 2x plus, and I heard it, 1/8. The plus becomes a minus cosine of 2x plus c by the old u sub. There it is. There you don't have to factor out anything. Man, that went great job. But you've seen it all. What if there's just a lonely cosine squared of x? Use this. What if there's an x combined with this? Still use power reduced 9w. What if you got sines and cosines? Play around with that, you gotta get a lonely sine or a lonely cosine. What if you have tangents and secants? What I like to do is get everything in terms of secant and then get the lonely secant tangent x. Although there are some situations we can kind of play around with that. Is that okay with that? Oh, and I apologize again for that. That's, by the way, that's this, I did that like 3 years ago. I was mad the entire day. Somebody upset the rest of the day. Just writing it on the board. I'm like, boy, I'll never do that again. I said that in 2013. What did I write up there? Freaking sign again. Hey, can I erase? Yeah. Everyone, that is section 7.2. So now your notes. We're going to begin section 7.3. We're going to begin section 7.3. It's still trig, but the title of this section is Trigonometric Substitution. Okay. So, can I erase this board here? Okay, I'm going to erase all this, entitled 7.3, Trigonometric Substitution. What happens in this section? You get a lot of stuff that's written like this, maybe inside integrals. You get stuff like this. I'm going to write stuff. Maybe something like this. Okay, or maybe something like this. These are the types of situations that will occur inside the integral. You go, well, how do you deal with that? We can use trigonometric substitution. Well, there's a cool table in the book. I'm actually going to present it right now. I want to let everyone know what page this is on. This is from page 478. All right? It's really very simplified. Trigonometric situation. This is the kind of stuff that's going to appear in the what? In all the integrals. You know, maybe integral dx, integral dx. I want you to see how you could recognize when am I going to need to use this section? Because the last section also had what in the title? Trigonometry, right? So I wanted everyone to be able to say, when am I going to use this section? You see things with these radicals, and maybe it's like x squared and x squared. Y'all notice the other perfect squares in there? Okay. So I'm going to draw triangles. Here's my first triangle. I'm going to put an x here and an a here. I'm going to write this as square root of x squared minus a squared. That's by Pythagorean theorem. Does everyone agree? If you see Pythagorean theorem, that would come out like that. That's the first case you'll see in this problem. And when you have something like this, what we're going to let x equal to? Oh, and put a theta here. I apologize. I'm going to put a theta there. What do you notice about sine of theta? Can everyone see that triangle? I'm going to write it really big over here. Theta. This is x. This is a. This is the square root of x squared minus a squared. What do you notice about sine of theta? It's a over what? So what would x equal? X would equal a sine theta by Secant. Do you all agree? Okay. Sure. Do you agree here that the sine of theta would be opposite over hypotenuse? Oh, cool. So if we get a scenario like this, we won't see triangles, but you'll see this expression somewhere. We can always just let x equal to a times sine theta. Now the reason is because what's sine of theta in a scenario like that? Opposite over hypotenuse, so a will just equal x sine theta. Cool. And I'm glad you asked it, because I want you to think like, there's a way you can just kind of make these drawings and just do Pythagorean theorem and Secant, right? I know. Here's another scenario, and I'll make sure to put this over there too. So it's sitting up there the whole class. Well, what if you get something like this? And you get an A here, right? And in this case, you have the X there. So you have an A here and an X there. Well, with this case, make sure I have that right. Oh yeah. I'm going to put A here. XA. X will equal sure one sees this. Sine theta equals A over x. So in this case, I'm going to rewrite this because that wouldn't work out, would it? No. So I'm going to draw this again. I'll make a nice clear triangle here. Right here. Yep. And I'll write the actual chart that they have. A squared minus x squared. I'll draw the triangle last. So no one's confused. We're going to use x equal to sine of theta. Alright. If you have a scenario like square root of a squared plus x squared, we'll let x equal a. And finally, if you have square root of x squared minus a squared, we'll let x equal a secant theta. And I'll leave some room here. In this table that I'm presenting here, you'll notice is on the textbook. It's in the textbook on page 478. I apologize for that last triangle. I want you to see these do involve triangles. So in this first case, sine of theta would equal x over a. So this would be square root of, by Pythagorean theorem, b squared plus x squared equals a squared. So what would that b squared equal? Square root of a squared minus x squared. This image goes with part 1. But you could check it over. So I want to see that the sine of theta equals x over a in that scenario. I'm going to write the triangle backwards. This section is not bad at all. What we're saying is that when we see these integrals with these radical expressions, this is the substitution we're going to put. That we're going to follow along. We're going to follow along and use this substitution here, this substitution here, this substitution there. But I wanted you to see why, because this triangle, sine of theta is x over a. What would the triangle look here? Can you help me build this? Here, put a theta there. Well, tangent theta is, what would tangent theta equal? X over what? X over a, so what would this become by Pythagorean theorem? A squared plus b squared equals c squared, wouldn't you get that? And lastly, what would this triangle look like? I'll leave these triangles up here the whole time. And when x equals a secant theta, so what's secant of theta equal to? X over a. Remember, secant is cosine's reciprocal buddy, right? So when I do secant theta is hypotenuse over adjacent, I'll put x here, a here, and put the square root of x squared minus a squared. And put the theta here. But these triangles were not drawn in the textbook on this page. 478. But I encourage you in your notes to put those triangles because they're all related. There's something else I'm going to add at the end. If anybody's looking at a textbook now, you go, hey, they wrote something else here. I'll add that in a second. But those are the three scenarios. So obviously, when we see this in the integral, this is going to be our substitution. If I see this somewhere, these a's are constants. Please note that the x is the variable, the a is the constant. Cool. All right. We got it? We got it. Let me squeeze through here. let's get started. Let's look at a problem, everyone. This is from section 7.3. This is like number 1. Let's start off with a problem that's just like number 1. And I got the integral of dx over x squared square root of 9 minus x squared. And they want us to find the antiderivative. All right, so this is like number 1. Can you recognize which scenario it is? Man, you're good. So as long as we know this, these 3 situations here, if we're familiar with these 3 situations, when we see that radical expression that appears in the integral, we'll know exactly which one to use. So I'm saying here, that's a 9, so the a value will be, is a 9 or a 3? I'm going to let a equal 3. This is looking like this scenario, scenario 1, and I'll let x equal 3 sine of theta as my trig substitution. Okay, so I'm going to write that down. Let's let x equal 3 sine theta. Cool. Hey, real quick, what would dx be in terms of differentiating both sides with respect to theta? This is the first thing I'm looking at for this problem. Let x equal 3 sine theta. What is dx equal? 3 cosine theta. And what do I have to put here? D theta. All right. That's the first thing I'm going to check that off. I just want everyone to realize that. I know I'm going to let x equal 3 sine theta, but then dx would equal 3 cosine theta d theta. Great. Well, the second thing I wanted to look at is this funny radical. So let's write it again over here. And let's substitute. So I'm going to call this part 2. Before I go back to the integral. What would now the square root of 9 minus x squared become? Square root of 9 minus x squared now becomes, what can I substitute for x? This 3 sine theta. So you get the square root of 9 minus 9 sine squared theta. And I need you to help me simplify that. Everyone so far so good? How I put this here and substitute it? Yeah? Oh, yeah. So first of all, and hey Nicholas, you're okay with this part, right?
Yeah.
So now what I want to do, in each one of these problems, once I took care of whatever the x substitution is in dx, I want to find that radical part, whichever part it was, write it separately, but then use what I just used as my substitution and substitute for the letter x. This one right here. So this will become, I'm just going to put this is equal to square root of 9 minus, but for this x, I'm substituting a 3 sine theta, and then I got to square it. So a 3 squared becomes a 9, and then a sine of theta squared becomes a sine squared theta. So far, so good? Now, can you help me get this thing cleaned up?